Then the last type of isomers that you'll see, so this is only for these octahedral complexes where you have what's called, at least I've only known them to be called FAC and MER. So your book uses different terms that I'm not familiar with, but you could see where they derive them from. And I've only seen your book actually use these terms. But this is called a cis-cis isomer then. And so notice, right, cis, cis, so they're all next to each other. But the way I think about it, because it's called FAC, so it's kind of facial, so that means they share one face. And so you could think about drawing a plane, and all three balls would kind of sit on that plane. And you could redraw it too, to kind of help you see that. So I kind of think about orienting it. And those balls are kind of all down, so then they'd all be down. I can grab a molecule kit too if it makes more sense. And so it looked like that if you oriented it like so. And so again, all that face is the same. And so MER, you can see, well, you can see why the book calls it a cis-trans isomer. And so you have, right, trans, but then they're also cis to one another. And so that's where they got their name. I'm used to thinking of it where they're all kind of in the middle and you can draw a plane through them. So MER, kind of meridian. And so you can think, right, they have that plane going through all three of the ligands, giving you the MER isomer. And so on an exam, if I were to ask you about this, you could use either name interchangeably, cis-cis or FAC or cis-trans or MER. But again, this is one of those, just be aware if you Google, they probably will use FAC and MER. That's usually the more common language. But your book, again, uses those terms for some reason. And so kind of other isomers are what's called these linkage isomers. So one example of a linkage isomer is, so of course you can see this nitrogen is bound to the cobalt, but then it can undergo rearrangement just depending on the conditions, and then you have it bound to the oxygen instead, so that gives it different electronic properties. And so we can still have our optical isomers as well. So just our non-superimposable mirror images. So this is just one example. So we have our water ligands. So notice just drawing the mirror plane. If you were to attempt to rotate it, this, of course, water, would be back there compared to this one. So not the same. All right, let's move on to the fun stuff. So now we want to ask, well, where do the pretty colors come from? So, right, we can appreciate it and kind of previously, and that we could see that we changed the ligands, we changed the color. Oh, now I lost my, there it is, right? Changing the ligands, changing the color, but why is that? And how do we know kind of the electronic structure? And so we'll get into at least the most basic of that, which is crystal field theory. And so crystal field theory kind of gives us this look at the d orbitals and kind of how they arrange then based on geometry. And so we're just taking a cursory look at it. We're not going too deep, so you could really get into this. But the two main ones that you should be familiar with are the octahedral, which is shown here. And then I'll also draw out the tetrahedral splitting. And so all this is saying, so we have to think about it first, what we're starting with. So remember, this is our degenerate d orbitals. and probably think of that, right, as in our gas state. So your free metal ion, just hanging out, gas state, not bonding, not doing anything. And so we know the d orbitals start off as degenerate, aka all the same. But then once they go into their geometry and start bonding, now that starts changing the energy levels. And so what we see is the ones that are up here. So what we're actually looking at is we're looking at, these are usually kind of non-bonding. So these are non-bonding orbitals. And then the ones that are raised higher, so we're actually looking at the EG anti-bonding orbitals. So down low, not shown here, are going to be the EG bonding. And so that's going to be involved in bonding. And so let's look at kind of what orbitals these are, just again so you can kind of visually orient yourselves. So this is an octahedral complex. Doesn't really matter what it is. And let's just draw some generic balls on here. Yeah.
The EG, what does the EG stand for?
Doubly degenerate, but so that's why I'm saying we're only taking a cursory look at it. So I'll tell you where they come from, but it may be more information that you want to know too.
Might be more information I want to know. You have it up there, so if it's something we're responsible for knowing what EG bonding stands for.
Yeah, so EG is derived from here. So this is your octahedral point group. And so now this may be too much information, but this is kind of where it comes from. So this is why I'm saying we're only taking a cursory look. But how to break this down? So we're looking at what's called this character table for point group octahedral. And so that's saying, right, our geometry is octahedral. That's why we pulled this up. But then what's interesting is, I know it looks like a huge mess, but you can use it to tell you like what orbitals are involved in bonding. And so to break this down like kind of simply without getting too much into it, so if you look, you have your x, y, z here. And what this is, these are your p orbitals, x, y, z. And so we're not invoking them in bonding. And so they're called T1U. All that means is they're triply degenerate. And so they're not involved in here. And so, right, they're not even on here. Is this the right button? And then, so looking back, so now you have all these kind of messes. And if you look, so these are supposed to be your d orbitals, except they have different mathematic functions. So these are your x, y, yz, yz, d orbitals, so T2g. So those are there. So that's where they come from. But since, right, they don't match up with our p orbitals, so we would want these if we were trying to match with p orbitals. So these are non-bonding. So that's why I just drew them as non-bonding. And then what I'm trying to get to is, well, why are these kind of invoked in bonding? And so you see it here. And what's confusing is they don't just have z squared. They have this x squared plus y squared plus z squared. But this is your z squared, so whatever one matches. And it should be highly symmetric, and it is, but you don't know that yet just because that's not the nature of this course. But A1G means fully symmetric by rotation, and the A's all mean stuff, but we don't need to go into it, but it just means fully symmetric. And so that's why it matches up. So, right, you're fully symmetric, matching up with kind of your balls. So now it's just like, think about it more simply of pictures now, of happy pictures. And then we have our x squared minus y squared. And so that's hidden in here, x squared minus y squared. I think I misspoke, so ignore this one. Sorry, ignore this one. This one is our z squared. I'm sorry, I said that wrong. So this is z squared. This is x squared minus y squared. But then for octahedral, that means that they're the same energy level. And so that's why they're called EG. And so we have, right, these two kind of coming together. Where are d orbitals? And so just write a refresher, x squared minus y squared, and dz squared. So those are the two degenerate ones that are the same energy, and the ones involved in bonding. And again, just appreciate, right, the pretty pictures, that they're in line. And so they would have to match the coloring. So it would look something like this, out of phase, in phase, and then in phase, out of phase, but of course in phase with that. So those are the pretty pictures kind of coming together. So that's all we want to kind of get from this one. So that's our octahedral. And so now let's compare. So you could, of course, do a splitting diagram for every compound. But again, we're only focusing on two. So you could also look it up too, like what's trigonal bipyramidal? What would that look like? And the internet will tell you. Or we could do way too much chemistry than you would want to know. And you can learn how to use character tables. But the other one is tetrahedral. That is, again, most common that we'll care about. And so we start off with our 5 degenerate ones again. And then let me pull up the square planar, or sorry, it's tetrahedral. And so the funny thing about tetrahedral is it's the exact opposite of octahedral. So now these two are on bottom. And so those are going to be your formally non-bonding, so z squared and x squared minus y squared. So those are non-bonding. And then your T2G is the one involved in bonding. Or actually it'd be T2. So now looking back over here. So now this is a character table for tetrahedral, so TD. And this might help you understand why we're invoking these d orbitals. So if you look and try to orient ourselves again. So this is our z squared and our x squared minus y squared. So that's E. So in this case, and they have different labels too, so it depends on what functions they can do. So this is just E now, so it loses the G label for reasons we won't get into. But then if you look at T2, you can tell that it's going to match with our p orbitals, since it matches, so you have x, y, z, so this is px, py, pz. But then this x, y, yz, and yz match up, and so that kind of helps us see that they're going to be used in bonding then. And so that's where that came from. And so now we can just write x, y, yz, xz, so just knowing that's where they came from. And remember, this is the anti-bonding one that we're actually looking at. And the bonding is down there. All right, so now let's relate it to, well, how do we get the pretty colors? And so if you recall back to first chapter, remember we looked at energy and light and the relationship. So we had this energy equals Planck's constant times the wavelength. We could also write HC, or sorry, Planck's constant times the frequency. Or this other equation, right? Planck's constant times speed of light over the wavelength. And so this energy, the color then that we see, is equal to this band gap. So whatever the difference in energy is here, we'll see a pretty color. So all these tend to be kind of lower in energy as well, so they're in the visible region. We get a pretty color. We could hook that up to a spectrophotometer, right? Get the wavelength or whatever we're interested in, see the absorbance, and then measure that energy. So that's how we can kind of start quantifying that. And so the other thing we want to identify, and we'll look at this, is we'll look at problems, and then it may tell us some information, like it's paramagnetic, diamagnetic, and then we have to determine kind of what state it is, and we'll look at kind of high spin versus low spin. So this would be just very simply, right, ground state versus excited state, and we've seen that before, but just know you can have those types of energy promotions, again, just like we saw in the hydrogen atom. And so let's look at this. So now we're looking at the absorption spectrum of our hexaquo titanium 3 compound. And so the absorption of the photon in the blue through orange region excites the d electron from the lower energy T2G set of d orbitals to the higher energy EG set. All right, so let's do a problem. And so looking at this, it's about 480 nanometers. And so what then is and so this energy is called the octahedral field splitting energy, just shown by this little delta circle here. So what's the octahedral field splitting energy then of titanium hexaquo compound here? All right, I'm going to go through it just because I want to get through high spin, low spin stuff as well, and that takes a while. So we can plug it into our formula, E equals hc over wavelength, and so again, this should all be old information, but h was Planck's constant, so 6.626 times 10 to the negative 34. And so that's meter squared, kilograms second for those units. We need the speed of light, so 3 or 2.99 depending how you're feeling that day. And then I'll just put this in meters, so don't forget to put that to meters. And I'm going to do what I call my lazy conversion. And so then we can plug that in. Times my speed of light. And so hopefully you got the energy, something like this. So as long as you're somewhere around the order of magnitude. And then don't forget that that's joules. So questions about this?
What is the 480?
Oh, that was just, I just picked it as the spot where we had the most absorption roughly, and then so 480, this was nanometers, but then we had to convert it to meters, so I just did what I called a very lazy conversion, so just multiplied it times 10 to the negative 9 for that factor. Other questions about this? Again, you can dig back to your first quarter knowledge or review your energy wavelength. All right, so the last bit, and really what's kind of important in this chapter, is this high spin, low spin designation. And so what happens is that, right, you can have different splitting energies kind of based upon the ligands and what's actually attached to it. And we'll go into what kind of the trends. But the big question is, well, how do I identify, again, what's going on electronically? And then what does this mean, low spin versus high spin? And so if we look at what this means, so notice in our first example, our octahedral splitting field energy is relatively large, right, compared to the second one. And so if this energy is large enough, that basically means it's unfavorable to put this electron into that higher orbital. So, right, you're trying to kind of determine, well, what do I have to pay a greater energy price of? Because remember, we have that energy price of pairing that we have to pay. So that's not favorable. But if you have to put more energy in to promote it, right, that's also unfavorable. And then do we remember our terms diamagnetic, paramagnetic? See some nods. And so, right, quick refresher. So if something is diamagnetic, I can't ever spell. So that means it has all paired electrons. And so because a compound is diamagnetic and they're all paired, when you put it through an NMR, and this is how you determine it experimentally. So if you put a diamagnetic compound in the NMR machine, then it's going to be like really sharp. And what we mean by that is like the peaks are well defined, they're sharp, you can see everything. And so that tells you that your compound is diamagnetic. And let's say you stuck it into the NMR, and instead it looks blobby and maybe spans a huge range. And so that means that you have a paramagnetic compound, and that means you have unpaired electrons. And so then kind of from this information, and then also, you know, probably you would need a crystal structure, or at the very least, you know, some idea of what your structure is. From there, you can determine, is my compound low spin or high spin? potentially. And so let's look at some more examples. And so now we're comparing. So let's look at these. So what's my oxidation state of iron? What do we say? 2 plus. There we go. And so now we're comparing, so let's just say we're comparing these two compounds. Maybe we stuck them in an NMR and got some information. And so now we're trying to figure out, what's the difference between them and how we distinguish. And so that's the first key, right? So they're both iron 2 plus compounds. Okay. And they both have 6 ligands on them. So they're both octahedral. And so now depending, right, on what you're kind of doing, maybe you sketch out the octahedral crystal field splitting diagram. And all that is, you don't have to get too into it, but just write T2G, EG, at least 3 on bottom, 2 on top. So that's your general structure. And so if it's 2 plus, what D is it? Because this is where you also fill in your D electrons. So look back at your periodic table. So what big number is iron in? And then it's 2 plus, so take 2 back. So you said 6, right? So 6, exactly. So D6. So then the trick is it going to pair up and not promote? And I'll just kind of rewrite what they have. But basically, you're trying to determine, is it going to go 1, 2, 3, 4, 5, 6, meaning that octahedral splitting energy is too large. It's not going to do it. And then notice what this gives you. So this is called diamagnetic, then diamagnetic. And so you would be able to tell by the NMR if it was, then in this case, low spin. So low spin meaning it's not promoted, they're all in the lower energy levels, versus your other possibility. So let's say it will promote instead of pairing first. So 1, 2, 3, 4, 5, 6. And so now in this case, you would get a paramagnetic compound if it is indeed high spin, and you would plug that into the NMR. It'd give you this horrible looking spectrum, but then you could tell, oh, that's paramagnetic. And so that's part of the trick here. And so maybe on like a quiz, you'd be either asked to fill in the diagram, what does high spin paramagnetic look like, or some sort of comparison of those two diagrams. And, well, now you might be asking, what drives this? Yeah.
So, on the B sketch, why did we go up top? Because on the A one, you just at the bottom, it's just it's high spin, so.
Yeah, so if this is high spin, that means that this octahedral splitting energy level is smaller than whatever price you have to pay to pair them. Yeah, so that means it's more energetically favorable to be in these higher energy levels, again, because his gap is small now for a high spin compound. Yeah, and you can only determine this, like I said, experimentally, right? Or else you're just going to be debating between these two. So you have to have some additional data.
So if this was like on a test, you would tell us if it was high spin or low spin.
Yeah, or something, or like, oh, it's paramagnetic, and then you tell me whether it's high spin, low spin. And then what drives this general trend? So now these are like how how the different ligands influence the splitting diagram. So if you notice your like kind of halogen ligands, so these all tend to be high spin compounds, so low energy barrier. So again, you see that with the fluorine. And so those are like your 1 electron donators. And then as you kind of increase across this spectrochemical series, and this was just determined experimentally, and again, it just depends on ligand strength. And now, as we go over to kind of more L-type.
Is that why we were able to go from water to ammonia to cyanide?
Yeah, so then they become more binding too. So I don't want to get into all this, but like these tend to do what's called pi back bonding. But if they can pi back bond, it just basically means they can make more bonds, and that changes your energy level. So then that's going to make it more unfavorable, actually. So if it's pi back bonding, then your anti-bonding, since you're looking at the anti-bonding, which is kind of confusing. But if this is anti-bonding and your pi back bonding, this actually gets even higher in energy because it's now worse, right? Because we're not looking at the energy we save down here. We're looking at our anti-bonding. So now more bonding, higher in energy, but then it's going to be low spin. But I wouldn't stress as much about like memorizing this or anything. It's going to be based on whatever evidence I give you on an exam. So we're like almost out of time. Let's look at one example. And so let's look at this nickel tetracyanide species. And so its overall has a -2 charge, and it is square planar. And so give me the D count and then just a comparison of high versus low spin, and then you can tell me, right, how to determine it. So which would be paramagnetic, which is diamagnetic, what am I looking for? Oh, I don't want to do square planar. Tetrahedral.
What percent of our grade is the exams again?
Oh, I would have to look at the syllabus.
That's fine. Don't worry about it. I just wanted to know if you're one of those classes that just has an easy rule where it's like 60% of the blah, blah.
So since we're kind of out of time, let's go through this. What's the D count? Or, is that what you got for oxidation state, 2? Yeah, so nickel 2, and then what's the D count then? So D8. And so then all we do is fill it in. So if we wanted to do, so let's just compare. I'll just put low spin over here. So filling up 8. So 1, 2, 3, 4, 5, 6, 7, 8. Versus a high spin compound. So 1, 2, 3, 4, 5, 6, 7, 8. That one didn't make a difference, huh?
There just wasn't enough flow energy.
Yeah. I made a bad example. So in this one, right, this one would probably be no difference, obviously. So that one, if I had given you this bad example, you would just say, right, no difference, you couldn't tell. Or really, right, it's the same configuration. So no difference, but yeah, that didn't work out because it's not actually tetrahedral. It's square planar, but then I didn't give you all the square planar splitting fields, so my apologies. All right, I think for the sake of time, we have to stop and then take our 10-minute break, and then we'll do our quiz. And we'll probably do more examples of this next week, so I don't leave you hanging